All right, next up on the agenda, we have Meredith Beveridge of ASI by Rocketlab, presenting on a microservices-based flight software for distributed constellation autonomy. And Meredith, do see your video and yep, all yours.
All right, thank you. And you can go and advance to the next slide. So hello, everyone. Day 3 of a virtual conference late in the afternoon. I'm sure you're all super psyched and full of energy. Luckily, I know these are all being recorded, so if you missed something crucial, you can go back and check it out later. I saw some names I recognize on there. Nice to see you all. I hope to see you in person someday soon. A lot of people out there I've worked with and enjoyed working for as well. I've been in embedded software on resource-constrained systems for about 20 years. Recently been doing flight software on spacecraft. So I have some software currently orbiting Earth and Jupiter right now, which is pretty cool. I'm now at ASI, Advanced Solutions. We're over in Littleton, Colorado. And today I'm going to talk about some neat new features we've done with microservices architecture, as well as autonomous solutions. That's part of our modular autonomous extensible flight software, MAX flight software, which is flying on, I think the current count is 49 spacecraft right now. And it's a truly reusable heritage software that we maintain constantly and do regression testing every night. And so we really achieve the reuse that we all strive for, rather than just copy and pasting some lines of code and calling it reuse. So I'm very excited to be here and showing you some of the cool things we're doing. We were recently bought by Rocketlab. So we're at the beginning of their Denver location and part of their build up to providing spacecraft for the full end-to-end space solution for their customers. All right, so you can go to the next slide, please. And the next slide. So microservices is kind of a buzzword lately. It's the concept of a distributed architecture where you have very tightly scoped services. So micro doesn't necessarily mean small footprint. It means that you very carefully define the scope of a piece of software to do a very specific feature within the system. And then you have many services usually that accomplish the full mission, and they talk typically over a pub-sub bus. So in this example, I'm talking in particular about how we've created some services for DARPA's Blackjack program for the pit boss in particular. But we also have some other items in our MAX flight software that can be microservices, such as our command telemetry module, our ADCS, and our Odyssey simulation models, which I'll talk about a little bit more later. But I'm going to talk about these 3 that we did for pit boss. So this use case is a proliferated LEO constellation of spacecraft. So there's hundreds of nodes, and it's truly distributed in the sense that there's no master. And they're supposed to autonomously be able to execute a mission from a high-level user command. And so the 3 services we created were to help figure out how to accomplish that autonomously on board. And then the advantage of microservices architectures, if you're not familiar with it, is you can swap these things in and out as you have an upgraded version, or maybe you swap in a third-party version. You can add additional services like a new massless payload that's going to consume some data and produce a more sophisticated data product or something like that. In this example, we were working with probably a dozen other parties who were also providing services. And so each one could focus on our specialty, which for us is ADCS and autonomy. And for others was things like security and user interface and things like that. So each one of us provided our service in our little microservice, and they all talk together over the pub-sub bus. So if you go to the next slide, please. So the first service I'm going to talk about today is the Constellation database. So this is how we implemented the common operating picture. So this is proliferated LEO, which means they are all orbiting Earth, low Earth orbit, and they're all connected in a network. So in this case, it's a laser comm network. And so as you can imagine, as you move across the Earth, some of the spacecraft can reach certain ground stations and others can't. but you may be wanting to execute a task or a command on the other side of the globe from where the ground station access currently is. So you need to be able to get that data across the network to the nodes that are going to be in the region of interest during the time of that mission. So we have to be able to get data up to the spacecraft and proliferate it across the network, as well as get data from places that are gathering the data and sent back down to the ground or to other nodes that need that to do some sort of calculation. And so the way we did that was with a microservice that implements a distributed database. So again, there's no master. So everybody has a replicated copy of the database on own node, and they can generate their own unique IDs for their primary key for the data that each node is generating. And then you receive updates from your neighboring nodes all the time, as well as heartbeats from those other nodes. So you can tell when certain nodes go down, or even when your own node goes down. If everybody else's heartbeat suddenly is stale, then there's a good chance that I've lost the network. And we used conflict-free replicated data types, which is pretty cool. You should go Google it, which are key value pairs, and they allow you to individually update data within the database without fear of stomping on others. And then all of the different services can monitor this Constellation database. So if you go to the next slide, please. It's a pretty simple interface. There's getters and setters for the data objects, and then subscribe, unsubscribe. So if I'm a producer, I'm setting data in the database. And if I'm consuming some data, I would subscribe to that piece of data by its unique ID, and then get notified as soon as that's updated. So I can do event-driven tasking. And maybe I consume some data and produce more data products, which I then set into the database, and that gets proliferated across the constellation. So everybody has the same common operating picture, COP. And then we also used replication policies and retention policies to determine whether we want to keep all the data everywhere and forever, or do we only want it in certain spacecraft for a certain amount of time, or is it a FIFO or those kinds of things to manage memory as well as data integrity. So you can go to the next slide, please. The next service I wanted to talk about was the task allocation service. So this is some autonomy that we've built into our Max software. And this takes advantage of our access planning algorithms that we have. So the ability to map a field of view of a sensor with the ephemeris of the spacecraft and its path and orbit, and figure out when is this spacecraft sensor going to be in the region of interest that we want to take data on. Or maybe it's for comms or whatever kind of mission you're trying to explore. So like I said, the concept of this program for Blackjack is that it's a proliferated constellation with no master, and it's supposed to autonomously get a command from a user and figure out how to accomplish it. So this service takes that high-level user command and goes and breaks it down into tasks and figures out which spacecraft are going to be able to execute a piece of that task, and then scores it. So how well can I access that based on my field of view coverage and orbit parameters and things like that. Puts that data into the COP that we just talked about, takes the data out of the COP from the other nodes, and determines autonomously on orbit whether or not to participate in this mission. And then stores that status as well back into the COP so that the ground and the other nodes can know which spacecraft are executing the mission at any given time. And then you can go to the next slide, please. So the third one is a lot of our core Max software capabilities put into a microservice. So all of our fault management, all of our ephemeris calculation, different configured parameters where you want to balance things like power against bandwidth and thermal. All of that autonomous decision-making goes into this service to make sure the spacecraft is functional at all times, can communicate at all times, and stays healthy. And then, like I said, we have other pieces of Max that can be microservices, like our command telemetry module, our ADCS, and Odyssey, our simulation models, which I'll talk about a little bit in a second. So can you go to the next slide, please? And you can push play on this video while I talk to it, please. So this is just one use case of the autonomous software running on board. In this case, we're maintaining the network. So there's cross links between all of the spacecraft, and we're trying to keep as many of them up at a given time. But at the same time, we're trying to maintain power positivity. So we're pointing the panels at the sun. And there are times when you're gonna have to flip the bus, which is gonna break the links, right? So we autonomously predict both the sun pointing and the link pointing, the laser head pointing, to make the best decision on how to maintain the network as best as possible with as few links down as possible at a given time. So that was just one example of those autonomy services running on orbit. Next slide, please. So now I'm going to talk a bit about containerization, which some people I think talked about on a panel yesterday. It was pretty fun to see that topic. So if you go to the next slide, we've been using Docker for a while at ASI to do our cross compilation, which is really cool. So you can build it very quickly and automatically for different platforms, different OSs, so Windows, Linux, RTOSes, build it for ARM, build it for Intel. We really like that process. And then in this project, we also flew Docker on the flight processor. And in this slide, I'm talking about Odyssey, which I mentioned earlier. We can also put our simulation models within the container to make Docker think it's flying a full spacecraft and to make our flight software think that it's actually on a spacecraft. So Odyssey is our simulation model set that we use to simulate the actual flight software to make it think it's connected to all the peripherals and ADCS components of a spacecraft. And we test that way constantly. So in this example, we actually ran Odyssey with Max flight software in a container so that we could simulate an entire spacecraft. And if you go to the next slide, please. So what was so powerful about doing it this way is we were able to take one Docker file and spin up all of our containers and all of our partners' containers. So we can connect to the Docker registry and pull in everybody's latest images. They're all talking over that pub sub network in this microservices architecture. And so you can spin up one spacecraft node fairly easily using Docker registry. And then you can scale that up to hundreds of nodes. So now we've got hundreds of networked spacecraft running in a Docker simulation in the cloud. Well, we were also able to run a couple hundred on just one desktop. And so you could do all kinds of statistical analysis, performance metrics. We're able to run it faster than real time, so you can even do Monte Carlo and things like that. And then we expanded it to do ARM emulation, so you could have some of them running on a target platform or the emulation of the target platform. And then we expanded further to actually include a hardware in the loop test, so a flat sat running Docker, running all these containers on the flight processor, talking to all the other hundreds of simulated spacecraft in Docker containers in the cloud. So it was a very powerful way to test a constellation and to take a lot of really great metrics and statistical performance data on it. And then let's see, let's go ahead and go to the next slide. So I know this is a little bit of an eye chart and it's not meant to be a tutorial, just to show how simple it was to spin up 100. So it's very, very scalable. And we were talking about proliferated constellations, that's important. So just some little tiny snippets of what it took to just spin up hundreds of these spacecraft nodes. And then we could gather all the data from them, the logs and the, if they crashed, the crash dumps, command and telemetry, and keep track of that for regression testing, do simulations and scenarios and things like that. Next slide, please. So then I was going to talk about how we actually ran this on board and show you some cool stuff. So next slide, please. So somebody yesterday kind of stole my thunder with talking about GPUs, but it's great that this is getting more exposure in new space. So we're flying right now a satellite where we're doing a little demonstration of NVIDIA GPUs, and they're performing really well in LEO. So we're very pleased. I'm sure all of you who want more processing power are also excited about that. So we've been operating this at our location here in ASI for a year and some change now. We've got our MAX flight software flying on these things, and they're talking to different payload computers and doing some payload control and things like that. So if you go to the next slide, there's some more detail there. So this is showing how we're flying Docker. We've got some of those services I was just talking about, controlling payloads, controlling the bus, so actually causing it to slew and things like that. Massless payload on there, also running in a container to do some cool AI ML algorithms on board. So the payload computers here are your typical high performance GPUs from NVIDIA, and they're doing really well. And then they're all running MAX flight software and then talking to the regular flight computer running MAX flight software and having a grand old time up there. So up there on the corner is a picture of our ground data system software. So it's showing us some telemetry from a particular test where we were testing these containers running our autonomy services and controlling the bus that way, and controlling payloads and running a massless payload. So that's some flight data that's pretty cool. Next slide, please. So that's the content. I'm sure you may have some questions or comments. If you want to keep up with us, we have a really cool new demo series on YouTube that goes through all of our different products and how you can very quickly configure our flight software for a new spacecraft, as well as run our simulations and for your particular scenario and mission. You can also follow us on LinkedIn if you want to see how we're evolving into Rocketlab. And then, of course, on our own website, you can go through all our documentation and learn about all of our cool solutions and contact us if you would like. That's it. What questions have come up?
We've got a few, and looks like we've got time for some. So Meredith, thank you so much. That was a really great talk.
Thank you.
So we'll dive right in. So first question from Alan Mick. A question for Meredith about containerization. At my institution, we are moving from Docker to a different container technology, Podman. This is due to security concerns. Is this something you are aware of or concerned about?
So I am not involved with that selection. I think the concept was just the containerization, and Docker, you know how DARPA likes to use the latest and greatest commercial stuff. And so that's why they went with Docker. But I'm sure the other containers could do very similar cool things with microservices architectures. But thank you for bringing that up. That's a cool topic to look into.
Okay. Next question from Michael Garibay. How have radiation upsets been mitigated in GPU processing?
So in our case, we are able to take the approach of reboot once a day. We're in LEO, so we don't have major radiation tolerance requirements. We have not seen a whole lot of problems there, but obviously if you're going into a more severe environment, that's going to be a big concern. Okay.
Next question. Does Docker reduce flight software performance?
Performance was actually pretty amazing. So our flight software typically only consumes like 4 or 5% of the processor to start with, and then adding Docker only added about 1%. Memory-wise was very light. When you're all using the same lower layers, they all share that. So you don't really duplicate all of the OS layers if you're all using the same, say, Ubuntu 1804 or whatever. And then if you're using the same OS as the host platform, you save even more on memory. So performance was actually pretty impressive, especially for a resource constrained system like this, where we're always worried about that.
Okay. Next question from William Bergen. How do you manage the configuration of the entire constellation? Do you have an automated solution for on-orbit deployments or configuration management?
Oh yeah, that was really cool. So both for on-orbit, but also for the, even more so for the simulation, they all need to have independent spacecraft IDs, and some of them have different configurations. So we were able to, since we were doing this in Docker, we were able to just script the replacement of those particular unique items for a given spacecraft, and the rest of it is all the same. So it spins up the same containers, and most of them have all the same parameters, and you can just tweak the few you need in the simulation. And then on board, obviously you need to handle that very carefully. So yes, configuration management in the typical way where you have to handle that anyway, whether you're using Docker or not. And then there's,
okay.
I also didn't mention, we're running Kubernetes, so it can handle the resource management and dynamically spinning up containers if needed. It can recover containers, detect when they've gone down and restart them and things like that. So that's kind of a cool extra layer of fault management on board.
Okay. Next question. What kind of NVIDIA GPUs are you testing out in space, if you are allowed to say?
I'm not sure I'm allowed to say the exact ones that we're testing, but it's your typical latest and greatest NVIDIA GPUs.
Okay. All right. Next question from the chat is from Chris. Was the GPU Max setup a coprocessor system, or did it also directly control the GNC or health systems on board?
Okay, so that answer is all of the above, I guess. So we have firmware that does some very low level supercritical stuff, and then Max Flight software in this case is running on Ubuntu. So Linux is handling any of the multi-core issues. We're not explicitly doing anything in like CUDA or anything to take advantage of all that parallelization, mostly because Max Flight software does its thing. And if you want to do something really sophisticated, you'd probably put like a massless payload on there to do something like that. And then, but Max Flight software does do a lot of fault management. So it does monitor critical telemetry points and take action to safe the bus if needed, or to load shed or things like that. So multifaceted answer to that question. We could take it on Slack if you want to talk about anything any more detailed than that.
Yeah, I'm sure there's going to be some Slack threads about this.
Okay.
For sure. All right. Next question available from William Bergen. Have you considered building your own OS using a tool like Buildroot or Yocto and using that as a base image for your containers?
Yeah, and so there was a lot of discussion about what images to use. We did decide that we all wanted to standardize just for saving on memory and that sort of thing. But yes, there's a lot of fun things you could do with different images to save memory or to get particular features that you really want on board. And we can talk about that on Slack too, if you'd like.
Okay. All right. We have a few more minutes for questions. I'll give just another few seconds to see if any filter in. All right. Meredith, thank you so much for your time this afternoon. And yeah, thank you.
Thank you very much. Nice to see you all.